Good morning, sir. Today we are discussing commutation circuit. But before discussing commutation circuit, we have to discuss some important points about diode circuit. Some equations come out from diode circuits which we'll use in commutation. So our main topic is commutation. Okay. Now, in this diode circuit, we are assuming that it is contains a voltage source, diode, inductor and capacitor. In this, one assumption is that this capacitor is initially charged with 0 volt. Now at t is equals to 0, we will on this switch, and at that time this circuit is active. And while applying KVL, we will do Vs equals to Vd plus VL plus Vc. Vs equals to, that is Vd equals to 0 volt. We are assuming that diode is ideal. VL is equals to L di by dt. Vc is equals to 1 by C integration of I dt. By taking Laplace and then inverse Laplace, we will find one equation, and that equation is useful in commutation topic. So we will apply KVL in this Laplace in this equation, and after rearranging, we will get, and after that we will take inverse Laplace transform. After inverse Laplace transform, we will get this important equation, and in this equation we will assume this part as IP. This is constant, and omega naught is equals to 1 by under root LC, which will came from our Laplace transform. Now the final equation we will get I naught equals to IP sine omega naught. This is the important equation, and omega naught is equals to 1 upon under root LC. This is nothing but resonance frequency, and our current waveform is like this. At pi radian, this is touching to 0 axis, and at that time diode will be off and our circuit will be off. Diode will be off and our current will be 0. This is the duration. This is nothing but omega naught t. Omega naught is nothing but resonance frequency t, and this is equals to pi radian. T is equals to pi by omega naught second, and omega naught is nothing but 1 upon under root LC. So t is equals to pi under root LC second. So this we got important equation. This equation, this equation. This is a very important equation. Now we will move further. Now commutation are of two types: natural commutation or line commutation. It is only used for AC supply, and another is forced commutation. So why we require forced commutation? Because once thyristor is on and we have to off the thyristor circuit, we have to use forced commutation, because the current, DC current, never gets 0 automatically. We have to make it 0 so that it can touch x-axis and current will be 0, so that circuit will be off. So there are some techniques. Before discussing, we will discuss that natural commutation. Natural commutation is current 0, sinusoidal wave come to 0, and that circuit naturally commutated. Now there are 4 types of commutations: class A, class B, class C, class D. In class A, we will use forced commutation circuit, LNC equipment. Class B is current commutation. Class C is voltage commutation, or complementary commutation we also call it. And class D is also voltage commutation. Now we will discuss class A commutation. In class A commutation, we will use this is the circuit. This is the circuit where will get DC waveform, but we have to make it commutate it. So to commutate it, we have to make current 0. So to make current 0, we will connect L and C component. We are connected LC component, and this circuit is RLC underdamped. We want underdamped circuit. For underdamped circuit, we have one condition: R square is less than 4L by C. And by this circuit, we will again do our mathematical calculation, Laplace and inverse Laplace transform. We will get this equation. In this there is omega r, because this is underdamped circuit, so we are taking omega. This is a ringing frequency. The ringing frequency formula is 1 by LC minus r square whole L square, and delta is the damping factor r by 2L. Okay. Now we know that any constant is multiplied by e to the power of x minus x, that constant decay exponentially. Similarly, in our previous equation, this contains sine omega t. So this current will decay like this only. Now case number 1, if r equals to 0 and delta is equals to 0, in this equation if we put r equals to 0 and delta is equals to 0, so after r equals to 0, r equal to 0 means delta is 0, e to the power 0 means 1. Okay, so we will get this equation, and this equation is nothing but resonance equation. And in this we have current waveform like this. This is the current. When anode current is less than holding current, our main thyristor will be off and our circuit will be off. So this is the way by which we are doing commutation. Now our main important topic is class B commutation. Now for class B commutation we have main thyristor, auxiliary thyristor, LNC component, diode, our load. So here are three assumptions will be there. Now what are the three assumptions and why we are assuming that three assumptions? Any three assumption, Vc is equals to Vs volt. This is Vs volt at t is equals to 0 with this polarity plus minus. This is high inductive load, so that load current remain constant, and Tm is on at t less than 0. These are our three assumptions. Now mode first mode at t is equals to 0, due to in this mode the polarity of our capacitor is minus plus. So due to this polarity our diode will be off because diode is reverse bias, so it will not in our circuit. After that this is our source voltage and our current is going through load, and this is our LNC circuit which we discussed earlier, and this is the current which we have given IC, but the direction of IC and direction of this is opposite. So this IC is equals to minus IP sine omega naught t. This is the capacitor current. Capacitor is current is sine, the voltage is cos, because V is equals to 1 by C integration IDT. The integration of sine is cos. At the time ITM is load current. Now at the mode 2, as the capacitor discharges, it reverses its polarity, but inductor can't do current to change in any condition. Capacitor changes its polarity, and as capacitor changes polarity while discharging, the diode is forward biased because this is plus, this is minus. Now diode is come in circuit. Now while applying KCL, ITM is equals to I0 minus IG. ITM is the main thyristor current, I0 is the load current, and IC is this path current, capacitor current. When IC equals to I0, ITM is 0 and our main thyristor will be on. This is the main concept of class B commutation. Now these are the waveform. We will discuss which waveform so that we will clear all that thing. This is I0, which is perfectly DC current and highly inductive current. So current is constant. Now in first of all we discuss first T1 mode, first mode. This is our I0. I0 is our constant because this load current is going from this. IC is our sinusoidal current, which is already we discussed this LC component earlier, and after that this is our VC. First VC is our positive negative, and after that mode it reverses its polarity. So same only, first is plus and then is negative. First is plus and second is negative. So same is deflecting in our graphical representation. Now after that we are taken when IC equals to I0. At this point IC equals to I0, this current goes to 0. When IC equals to I naught, ITM is 0 and our main thyristor is off. That is our the main concept. Same only at this point IC equals to IC equals to I naught and this our ITM is 0, decays due to LNC component. Okay, now in this case when this is plus, this is minus, this is plus, this is minus, T is off. T is off in second mode because here is plus and here is minus. So it reverse biases auxiliary thyristor. Same only here, TA on here and TO will off here. Now our main point will start from here only. Now we will see as IC equals to I naught, ITM is 0, TM is off. So at IP sin omega naught T2 equals to I naught. This is the important. At IC equals to I naught, ITM is 0. IC equals to, so IC what we have discussed, IP sin omega naught T2 equals to I naught. Omega naught T2 is equal to sin inverse of I naught by IP and T2 is equals to 1 by omega naught sin inverse of I naught by IP. And 1 by omega naught is nothing but L under root LC. Omega naught is equals to 1 by under root LC. T2. This is duration of second mode which we find. This is the duration of second mode. First mode duration is pi under root LC. First duration mode is pi under root LC and this is the duration of LC sin inverse of I naught by IP. At the end of second mode, we are discussing that in this condition thyristor is off, but at that point reverse voltage is applied across the thyristor. That what was the reverse bias voltage? We have to derive that reverse bias voltage derivation. Now at the end of this, Vc equals to Vs cos pi plus omega naught T2. Why pi plus cos omega? Because this is pi plus omega naught T2. This is pi plus omega naught T2. Pi plus omega naught T2. Now pi plus omega naught T2 is minus cos omega naught T2. And omega naught T2 derivation we also know sin inverse of I naught. So we will put here. Let VR be the reverse voltage magnitude of the capacitor at the end of second mode. We have written reverse now, so we will vanish that minus sign and we will get final this equation. So this is the reverse voltage we applied across the thyristor after turning off. At this point main thyristor will off and our job is done. This is the point where reverse voltage is applied. The point where reverse voltage is applied, this is known as circuit turn off time, TCM. Now we will discuss about TCM. The time for which the circuit is our thyristor is reverse bias is known as TCM, circuit turn off time. Now this is the third mode. After turning off the thyristor, the load current will flow from here. As the load is highly inductive, this will only inductive current will flow. So Vc is equals to 1 by C integration of I dt. I is nothing but load current and it is initial condition that it is VR with this polarity. This polarity is different from our reference polarity. So we have taken minus because our reference polarity is plus minus and it is plus minus. So minus VR. At T is equals to TCM, Vc equals to 0. Let's see. At T is equals to TCM, Vc equals to 0. This is the TCM and Vc equals to 0 at that point. Same we can done here. At T is equals to TCM, Vc equals to 0. So Vc is 0 and from that we will get TCM, circuit turn off time, CVR by naught. This is very much important equation. Now we will move further. So we have to find what is the thyristor peak current. Thyristor peak current is I naught. This is the thyristor. While we selecting the thyristor, we have to take care that it can carry I naught current. ITA, auxiliary thyristor peak current, Vs under root C by L. This is the current which our auxiliary thyristor can sustain. The time required to turn off the main SCR After the auxiliary thyristor is switch on, to switch off main thyristor,